there are a lot of exceptions in the pattern, we don't call it a law. You know, a law is something that's going to have no exceptions or very few exceptions. We don't want too many exceptions in the law. But if you have a lot of exceptions, like exceptions, what I mean by exceptions is, well, it doesn't really work for this, or it doesn't really apply to this, right? If you have a lot of exceptions, we don't call it a law. Do you know what we call it? A rule. And so we have rules, which will have a lot of exceptions, and we have laws, which don't. But we could stop here, and that would be good enough. But then, even though we can apply the pattern, you know, we just say, okay, just keep shrinking this way, or keep growing this way. Right? It's a pattern. But we'd want to know a little bit more about that. And so the next step here would be a more fundamental description of what's happening. You know, why are we seeing these weird, you know, why are we seeing this kind of behavior in the size of the atoms? And this is where the hypothesis comes. Once you see these observations, once you see the law, then you can start thinking about this, a hypothesis. What a hypothesis is, it's a tentative, fundamental description of what's going on. And so what's going on with these atoms? What's causing them to shrink and grow like this? That would be the hypothesis. It's tentative because tentative just means does it have widespread acceptance or not? Once you come up with some kind of fundamental description where everybody goes, oh yeah, that appears to be correct, then we have something called a theory. But typically, you know, people don't say, oh, that seems to be correct. They test your hypothesis, you know, and make sure it's consistent. And so a theory is, one, it's going to have a widespread acceptance. So, accepted. Now, what I mean by accepted is it has general widespread acceptance. So it's accepted fundamental explanations or description of what's going on. Okay, not only does it have to have acceptance and have to explain things at a more fundamental level, it has to be able to predict. Be able to predict new, unforeseen observations, or, you know, results. And so we could go to some application of physics. So Newton, have you heard of Newton? Not this Newton with a K, but the Newton with an N. Have you heard of Isaac Newton, the physicist, mathematician? Isaac Newton, you know, the story goes that an apple fell from the tree. Have you heard that, right? All right, so what came first? The theory of gravity. Did Newton hypothesize the theory of gravity and then observe the apples falling from the tree? Or did he start with observations of the apple falling from the tree, which led to the theory of gravity? Well, he started with the observations. You know, with these observations, then he could, you know, time this, determine the speed, et cetera, et cetera. And so he observed things falling. He got the patterns, and he looked at the patterns for some kind of mathematical relationship, and he found them. The mathematical relationship, these are called the what are they called? Newton's laws of motion. Have you heard of them? Force equals ma, etc. All those are mathematical equations that fit all the graphs he made for this. So we have Newton's laws of motion, but you don't stop there, because if you stop there, you could use Newton's laws of motion to get to the moon and back. You don't have to understand the fundamental underlying, right? But with these, you can, well, maybe you do need to know a little bit about, what was the hypothesis? The hypothesis was that there's some kind of attractive force pulling these to the ground, right? And that attractive force is gravity. So we have a gravitational theory. That's in physics. What about in chemistry? In chemistry, I just told you about atoms, but why should you believe in atoms? Are you going to take my word that there's something, this 53 picometer thing that called atoms? No, in science, the way science works is science is, there's no answer key. There's no, okay, let me look up the answer. I'll look up, do atoms exist? Let me check the answer in the solutions guide. There's no solutions guide, right? And so the way that scientists find the right answer is they just open it up for criticism. And if it survives all that criticism, then, it can progress. It doesn't mean it's right. Sometimes it does survive and it turns out to be incorrect in thinking, but essentially it leads to the right answer. And so, where did this whole idea of atoms come up? A lot of people never question the existence of atoms. Everybody takes that as a given. Things that are taken without proof are called postulates. And people don't really like taking things without proof, right? Because you want some kind of evidence to support this. And so, atoms. When were atoms proposed? Does anybody know? How long ago did somebody come up with the whole idea of atoms? That matter, the physical material of the universe, is made up of atoms. Your guess be? Well, around the 1700s is when the first kind of meaningful proposal for atoms came about. And so what kind of proof did they have? Did they all of a sudden, out of the blue, said, I'm going to hypothesize the existence of atoms, these things you can't even see, they're so small? Did they hypothesize that? No, it wasn't some out of the blue hypothesis. What they observed, they saw certain things that led them to hypothesize the existence of atoms. And do you know what led them to hypothesize the existence of atoms? It's this. The observation that led to atoms was something that happened in chemical reactions. A chemical reaction would be like a burning candle. That would be called a combustion reaction. And so if we look at a burning candle, the candle's mass is going down. I mean, the candle's getting lighter and lighter. It's getting smaller and smaller, right? The candle seems to be disappearing. And so the candle's mass is going down. And so that matter appears to be being consumed. But what they did was they did some very careful observations where they burned a candle inside an enclosed container. And you know what they determined? They determined that the mass of everything before igniting the candle and the mass after igniting the candle were exactly the same. Nothing changed. The mass before and after are the same. And so when you burn the candle, before and after, the candle is now just a little piece here. But when we measure the mass, and mass measures what again? Mass measures the quantity of matter present. And so here, the mass before and the mass after are the same. But what you have to do is you have to take into consideration, the gas, the air in the container as well. Okay, they did this for lots, not just burning candle, but for all kinds of reactions, chemical reactions. And They always observe the same pattern without exception. They always observe the same pattern without exception. Do they call that a rule, or would they call that a law? They'd call it a law. They call it a rule if there were more. And so this pattern was reproducible over and over again. And so they came up with a law. The law is very simple. Mass before is equal to the mass after. So we don't even need to write a mathematical equation for that law. But instead we give it a name. The name of this law is the conservation mass. Well, if it's conservation of mass, then it's got to mean conservation of matter. So this is the law of conservation of matter. Matter, and in fact, there's lots of ways of stating the conservation of matter. And one way is matter is neither created nor destroyed. And so why they came up with atoms? They came up with atoms because these atoms can just be rearranged. If you have atoms in the candle, those just got rearranged to atoms now in the gas, etc. And so that's why this led to the hypothesis. In other words, that matter consists of atoms. That was the hypothesis. But if you're in the 1700s, you don't have super expensive instruments. Nowadays, no scientist disagrees with this. Atoms exist. There's no doubt about it, because atoms can be pictured using sophisticated instruments. Single atoms can be manipulated. There's so much evidence that if you're a non-believer in atoms, then you're considered fringe, just totally out there, because there's just overwhelming evidence for the existence of atoms. But in the 1700s, did they have that? The 1700s, they're like the geologists out in the field. They can't plug anything in or see anything, right? And so how, if you're a scientist proposing this, the guy who proposed this is who really came up with the first comprehensive is a guy named Dalton from the 1700s. If you're Dalton, what proof do you have? You have this burning a candle. Is that going to prove to everybody that atoms exist? Things you can't see? No. So during Dalton's time, a lot of people were still disputing the existence of atoms. A lot of people were saying that matter is infinitely divisible. What's the smallest piece of copper you can have? Infinitely small, because all you do is you cut the piece of copper smaller and smaller. So if you start off with a little chunk of copper, you can get ever smaller chunks of copper. Whereas if atoms exist, you can't do that. Eventually you can keep cutting it smaller, and then you'll end up with one atom of copper. And then you try to cut that into a smaller piece, it's no longer copper. Right? And so we need a little bit more. And so what in the 1700s, what had to happen is it had to be able to predict new unforeseen or unforeseeable, I should say unforeseeable observations. And the unforeseeable observation that it predicted is this. It predicted that there should be a law, and this is the law of multiple proportions. The law of multiple proportions says that atoms combine in simple whole number ratios. So an example of the law of multiple proportions would be water. Water consists of two atoms of hydrogen, one atom of oxygen. Let's say I'm on a low oxygen diet. I want to be on a low oxygen. I don't want too much oxygen. Too much oxidation going on in the body. So I want low oxygen water. So can I get low oxygen water? Maybe H2 1.5. I'll cut down my oxygen intake a little bit. Is that possible? No. But if matter were infinitely divisible, then I should be able to get any amount of oxygen I want, because if I just want a little bit less, let's say I just want a hair less, I could go 1.9. But it doesn't work that way. It's going to be in simple whole number ratios. So another we call these compounds. Another compound of hydrogen oxygen would be hydrogen peroxide. You know, hydrogen peroxide is two oxygens. Now, if I'm on the low oxygen side, I definitely do not want hydrogen peroxide, right? Did you hear you probably heard this joke, but have you heard the joke? You know, they're quite a bit different, water and hydrogen peroxide, right? So the joke goes like this. Two people go to a bar. Bartender says, "What will you have?" First person says, "I'll have an H2O." And then his friend says, "I'll have an H2O2." And his friend died. That's the end of the joke. Anyway, we'll take a break now and then continue after the break. But we'll talk about the